Welcome to all of you who have joined us today in our mathematics education seminar. It's a monthly seminar with speakers from mostly from the Netherlands and sometimes a little bit abroad, like Flanders. Where we have a presenter and then discuss on mathematics education. I see some new faces, so very happy always to see new faces. Also always very happy to see old faces. I mean, familiar faces. Our speaker for today is Sanne Willems, who's an assistant professor at Leiden University in methodology and the statistics unit of the Institute of Psychology. And she specializes on statistics and in particular on the communication of statistics, which is actually very close to education because is education not a very special way of communication? So we're very happy to have you here, and we're looking forward to your contributions. So the floor is all yours.
Okay,
Welcome,
thank you,
Sanne.
Rogier. I will start sharing my screen as well. So I may have read the abstract, but I'm sort of presenting two topics today. It's on two different studies that I did. Can you now see my slide? Okay. So I'll present two studies with different people, and they're both on the communication of statistics, or at least related to that. So the first project I did was with Casper Albers and Jonica Smeets. Casper works at University of Groningen and Jonica Smeets here at Leiden, different faculty but same university. And we wanted to study the variability in the interpretation of Dutch probability phrases, because it was studied in many languages, but not so much in Dutch yet, or it had been a while. So we wanted to repeat that study, but then in Dutch. So, okay, we use a lot of probabilities in everyday life. So to make a lot of decisions. So for example, should I bring my umbrella? You're going to check the weather forecast. And then you decide whether you should bring your umbrella. Probably today it was a good idea to bring it. And this is, if you don't make the wrong decision, that's not that bad. You may get wet, but it's not a very big issue. But there are also bigger decisions in life that are also based on probabilities. For example, the probability of experiencing a side effect from a prescribed treatment. So as a patient, you may have to make the decision on whether you're going to use the treatment or not, or maybe make a decision between several treatments. And then it's usually based on probability. So it's very important to make sure these are communicated clearly. So in this doctor-patient communication, the doctor's sharing the probability with the patient, but they very regularly use words for that. So for example, the doctor might say it is likely that you will experience a serious side effect from the treatment. And so they use the word in many cases. And this is okay as long as you have the same interpretation. But if the doctor, for example, has 60% in their mind and uses the word likely to express that probability, and the patient interprets this as 90% chance, then there's a very big difference, and the may also influence the final choice of the patient. So we wanted to know, like, what is there a lot of variability in these interpretations? Because if there is, it might be risky. There might be a lot of miscommunication. So what we did in the study is we first had to select the probability phrases because there are a lot of them. So we looked at previous Dutch research on the same topic. There were a few with very small number of words. And we also looked at English research and then translated those words. There's a lot of this type of research in English. And we ended up with a long list of 131 phrases, but that's a very long set for one survey to ask all these similar questions about it. So we wanted to reduce it again. And we decided to choose those with more than 100 appearances on nu.nl, because then they were frequently used in news items. And this reduced our list to 29. So we focus on these 29 phrases. And we also removed one or two because we didn't want to have too much overlap with the previous Dutch studies. So we ended up with 29 phrases, and that was a nice number for a survey. I wanted to first do something interactive for you. So, and there are not so many people here, but we can still try it. I want to, if you go to menti.com and then type in this code, a question should pop up, and you can give your interpretation of 3 probability phrases. And I think it should be open. Oh, I have to press C to open the voting. It should be open now. Yeah, I see votes coming in, so it's working.
Yes, I can see it.
Let me move this to the screen so you can see it. The results. Okay, how many are we? Yes, I think we're ready for 1 or 2 more. Okay, so let's have a look at what you think about these phrases. Yeah, so there you have sort of different opinions and stuff. So likely is chosen, like I'll just list them 50% by one person, but most people are in the higher range, around the 70, maybe 80%. So, but there is quite some discrepancy between this vote and the others. Here there's sort of all over the place, but on the top half. And rarely you sort of agree. It's like most of you think it's below 10%, or at least below 20, let's say. So already in the small group, you see that there are quite some differences between the interpretations. So let's go. Oh, so yes. So this is kind of what we want to study. But now you saw these words, just the word itself, without any context. So, and that's what previous research showed, is that the baseline expectations within a context really have an influence on your interpretation of the probability phrase. So, for example, if you read the sentence, "It is likely that it will rain in Manchester, England on June the 2nd," in comparison to "It is likely that it will rain in Barcelona in Spain on June the 2nd, then you probably have a very different interpretation for this word "likely," because it's just a different situation, different country, and you expect a different climate. So context is quite important, and just asking you to give your interpretation of this word without any context was probably quite hard to do, because it really depends on the situation. So in our study, we did include context in the sentences. We gave people a sentence with the word included, but we tried to keep them sort of neutral, so that there was there was not too much baseline expectation. So, for example, the first context was, "It is likely that this plan will succeed," but we don't say anything about what type of plan it is, or what the background is. So, and also with "It is likely that the team wins the match," we don't say which team. So it doesn't matter which football team you support. But we wanted to include some kind of context to give some context for the words, instead of just giving this random word. So the questions were similar to what you got, but then with those sentences around the word. And then for the results, we first checked whether there were any contexts that had very different results from the other context. And here in this plot, you see all the 29 phrases. We translated them to English for this presentation, but they were originally the Dutch versions of this. So those are all the phrases, and these are the mean numerical interpretations, so between 0 and 100%. And then all the colors indicate a different context. And then all the dots are the means per combination, so per context and phrase. And you see that the dots, they are usually quite close together. Some have a slightly bigger range, but the ranges were had a maximum of 20 percentage point difference. So we thought, okay, they vary a bit, but they are close to each other, sort of close to each other. And we also didn't find a structural difference that one context is always higher than the others or always lower. So it seemed that we sort of had chosen neutral contexts, which was our plan. So that was just more to check. So based on this, we decided to put everything on one pile and from now on ignore the context and just look at the individual phrases. So then we could look at either all the phrases individually. So for example, this is the result of the phrase high chance, grote kans. And you can make several different types of plots to visualize the results. So you can make a histogram with all these bars, and then you see a lot of detail. So we see the high peak at 80%, also 70, 75, 85, 90. Or you can make the histogram, the smooth version of the histogram, which sort of smoothens the whole histogram. Which gives you slightly less detail, but also makes it sort of easier to get an overall view of the interpretations. So this is the interpretation for high chance. And these are the interpretations for all the words. So 29 words again on the vertical axis, and then the interpretations on the horizontal axis. These are all the meanings, so there's a lot of numbers. You don't have to look at them all. And these are the percentiles, 95% to 95%. But the most important things are the plots, because that gives the most, like the first indication of the variety of these interpretations. We got a lot of comments about the plots continuing before 0 and after 100, but that's because of the smoothing. We could chop them off, but then you will lose some information. So we decided to keep it this way, and I hope with you being all interested in mathematics that you understand how this happens. But most of these people, for example, they probably chose 0 as their answer, but it's smoothened out to the negative values. Okay, but from these plots we can draw some conclusions. So there was some consensus for some words. So for example, for the words like never and impossible, then all the answers are quite close together. Same for always and certain. So when these are very, the words have very clear indication of what is meant, like something never happens, then people expect it to be a very, very small percentage, but still not everyone thinks never happens is 0%. So there's still some variation in there. But for most of the other probabilities, their variation is very broad. So for example, the possible runs from, 20% till 70, maybe 80%. Maybe is also a very broad range. So for most of the phrases, there's no clear interpretation for that. We just don't agree on this. So if we look at the example where a doctor uses the word likely, then it's definitely possible that a doctor has a 60% interpretation and the patient has a 90% interpretation, because this is all within the range that we observed in our data. So these big differences can happen in such a situation. We also compared our results to the...
Can I interrupt with a small question? What maybe I didn't pay attention enough, but to what people, what was your sample of people?
Good question. We posted on Twitter, so we don't really have a representative sample. We have, I think, a lot of highly educated people responded, and we also posted it to statisticians via the Society for Statistics in the Netherlands to also get the result of, like, see if statisticians have a different interpretation, which I think I put in a slide on that difference.
Okay, but these are the joint results for those two groups.
These are the joint results. Yeah.
Okay, thanks.
Yeah, and the sample size was around 881, I think. But a good point. I should include a slide on that. So we wanted to compare it to the English study, see if the interpretations for the English words are the same for the Dutch translations. And so this is a table from a study that looked at several of these type of studies. And then so these are These are all the columns are different studies focusing on the interpretation of the probability phrases, and these are the probability phrases that were studied in at least one of these studies. And then these are the mean ratings from those particular studies. So for example, if we look at very likely, very unlikely, we see that our mean was 11%, and it is within the range of the English studies, because that runs from 9% till 28%. So it is within the range. Also, the range is very broad. This 9% till 28, it's 20 percentage points. So it's not very hard to be within that range. Same thing holds for the phrase probable. For us, it was 67%, and here the range for the English studies was smaller. It ran from 64 until 75, but the Dutch version was still, the mean was in that range. But within the word itself, there's a lot of variation. So we didn't see very big differences from the English interpretation, for example, but also in the English studies, it was shown that it was a very broad interpretation. So also the means differed per study. Other things that were interesting is that we see those peaks at multiples of 10. So you see all these bumps here and there, and that indicates that people like to round to numbers of 10 if they give an answer. And also we saw the bumps at the multiples of 5, but those are more easily visible if you make the histogram of this. And you see the peak at 75, which is not very clear in the smoother version. But people like round numbers. We also looked at asymmetry in the data. So we included some phrases that have the opposite meaning. So for example, the word unlikely and likely, they are of opposite meaning. So you would expect them to add up to 100% if you like mathematically. But in our data, if we look at the means, then unlikely has a 16% mean, and likely had a 75% as their mean. So in total, it's 91%. So it doesn't add up to 100% what you would expect. So it may also depend on which word you use, whether you put it negatively or positively. That might influence the interpretation of such a phrase or the whole sentence. So we looked at this for all the words that had their opposites in the data. So always and never, they peak at 100% because always is very close to 100% always, and never is very close to 0% usually. So together they do sum up to 100%. And the likely and unlikely is the most extreme case where it's a bit lower. And there are two very clear exceptions: possible and impossible, and certain and uncertain. And for example, we think that this is a different cause because if you say something is possible, then the interpretation is that it could happen. The probability is bigger than 0, let's say. If something is impossible, it means that the probability is 0. But since possible can have sort of any interpretation above 0, this usually ends up, well, anywhere between 0 and 100. Adding 0% for an impossible on top of it, then you end up at around 50%. So, but this is more linguistic interpretation probably than we don't really expect them to add up to 100% in the way that we measured it. Had we asked people to give a range of the interpretation, then we may have noticed that they really give the range 0 to 100% and 0% for impossible. But we only ask for one number, and then you have to make a decision. So that's probably why possible and impossible end up around 50%, and certain and uncertain much higher than 100%. So we also looked at, we compared the answers from statisticians and non-statisticians, because we thought like maybe if statisticians work a lot with data and percentages, they sort of have a consensus about what the interpretation should be, but this is not really the case. Here in this plot, you see the answers of the statisticians in red and the answers for non-statisticians in blue. We have fewer statisticians, but still quite a lot. But you see that most of the graph is purple, which indicates the overlap, and only very small parts are either red or blue. So yeah, there's very little difference between non-statisticians and the statisticians. And even statisticians themselves don't really agree on the interpretations, because we still see very wide ranges for statisticians only. So it doesn't seem like if you work more with percentages that you get to some consensus together, which doesn't really surprise me that much, because we, as statisticians among each other, we don't really talk about the interpretation of numbers. We just speak in numbers or words if it's a more informal conversation. So we're never discussing like, okay, what word should I use for 10%? So then we never get to a consensus, of course. Oh. Did I miss one slide? No. Okay, so to summarize, there is a large variability in the interpretation of Dutch probability phrases. And so if you use those in communication, this may really lead to miscommunications. So especially in important life decisions, just using words is probably not a good idea. So what should you do? Well, there is an option to use also the numerical values instead of the verbal phrases. But as you may have noticed, numeric values are quite difficult to understand for many people. And they also might give a false sense of precision. Like if you really give a person a number, then maybe they really think that's the truth, and they don't realize that it's also just an estimate, and there's maybe some range around it. So they think it may be more precise than it actually is. So I think it would be good to focus more on innumeracy, maybe through math education, so that people will understand those numbers a bit better. So in practice, what you see now is that often with a report, where they use the phrases in the report, they include a table like this, where they indicate what type of probability they mean with that word. So that's a step forward, but it's still quite hard to interpret. And the table depends on the organization or the report. It changes in every context. So here, for example, we see that likely in this case ranges from 66% to 90%, but here 100% is also included in that range. So it also depends on the situation what table is used. And you may have also seen them in the patient information leaflets. We also use the words with an explanation of what it means, but here the percentages are very small compared to these percentages here. So it really, yeah, it's kind of hard. There's not one table. You really have to include a table per report, let's say. Yeah, so that's, I think, yeah, there's some more research. Oh, yeah, there's also research on maybe if you use the combination of a verbal phrase and the numeric value. But one study by Knop showed that if you combine a verbal phrase with a numerical value compared to only giving a numerical value, then the interpretation is very influenced by the verbal phrase. So the interpretation is much higher if you do include a word compared to just giving a value. So the combination is not really a clear solution. Another study showed that it also depends on whether you give the verbal phrase first or and then the numerical value, or the other way around. So that also influences the interpretation, apparently. So just giving a number together with the verbal phrase is also not the solution. So I would say let's focus on innumeracy and see if we can get it up to a higher level, and that people can more easily understand the values, so that we don't need the words anymore. But it's an ongoing thing. So this is the first part of the presentation. So I'm going to go to the other study now, but I'm not sure if you want to ask questions about this first or at the end. I see a question from Natasha. Yeah.
Yeah, well, maybe you said it, but I didn't hear it. Did you do it in Dutch, the words, or did you use the English terms?
The Dutch ones, yeah.
Okay.
Yeah.
And is there somewhere a list that you use that I can find, a paper or something with the words, the Dutch words?
Oh no, I didn't put it here. In the article, in the appendix, we also included the translations from the actual Dutch words that we used.
Okay, thank you. Yeah,
I can send a link to the paper through Rogier, maybe, if you want.
Thank you. Maybe some other questions?
Yeah, Pauline?
Yeah, I was thinking this was done in the Netherlands, and we know the Dutch people are quite grumpy and always pulling everything into the negative, whereas we have neighbors speaking the same language. In Flanders, they are much more friendly. They take everything very positive. Could it be that all the graphs will be pulling to another side?
It could be. Actually, we asked people whether they were Dutch or Belgian, but we asked the question wrong. So I think a lot of, if Belgians participated, they actually indicated that they speak Dutch, because our question was just phrased in the wrong way, because our intention was to also compare that. But yeah, since we're not sure whether all these Dutch-speaking people were actually from the Netherlands or from Belgium, we are not sure whether we can compare them fairly. In the end, we had very few people who actually indicated they were from Belgium and they spoke Belgium or Flemish, let's say. But we just phrased the question wrong. So no, maybe we have to do it again and then compare. That would be interesting.
Thanks. And Peter also has a question.
You're muted, Peter.
Yeah, sorry. Thank you so far for the presentation. I was wondering, you showed all kinds of histograms, and they in the middle they had a tail to the left. Yeah, in this one. And is there an explanation for that? Because I understand that in the upper region, the tail to the left, and in the under categories, a tail to the right, but in the middle, it's all to the left.
Yeah, that's interesting, because all the ones that are options to indicate 50%, they all have a tail to the left. But the ones that are more to the right, they just are to the. We don't really have an explanation for this. If you know one, it would be nice. But maybe we should ask a linguistic, if they know why this could happen.
Maybe the suggestion of Pauline, the serious interpretation of the Dutch, but I don't know.
Yeah. So then we should repeat it and then really ask both people from Flanders and the Netherlands and then compare. Yeah. And have a better representative sample. So this was just not very representative, of course. Yeah, but we don't know why this tail is to the left. No.
Sanne, and I have a small comment. Would you prefer comment now or rather go further? I don't know how much material.
If this comment is related to this, then
yeah, rather. I'm thinking about your statement at the end that like maybe we should come just to numbers, avoiding words at all. From what I see on this picture, it looks like that words, they actually have double meaning, and on one side they point towards probability, likeliness, and on another side towards certainty. So some words express more certainty and some words are kind of deliberately blurry.
Yeah.
With numbers, we wouldn't be able to get that.
Yeah, of course. Yeah. So numbers would give a false sense of precision. So I think studying the communication of uncertainty around probability, as like the probabilities, would also, you would have to communicate those uncertainties in a different way, because words already sort of include this. In just because you're giving a word instead of a number, you're sort of including the uncertainty. But if you're communicating numbers, then there should be a good way to communicate the uncertainty around the numbers, because you will lose that. Yeah, definitely. Or maybe give a range. Yeah, there's also studies on communicating uncertainty, but there's no final conclusion yet, unfortunately.
Yeah, so maybe it's actually good that we can express so tightly just in one word that we are not certain even about how possible it is. Yeah. Okay. In the meanwhile, Lonneke,
I saw.
Lonneke, I got a question.
My question is related to that, because why do we want a precise number for a word? So what is the advantage of having a number instead of a word?
Oh, I don't think we necessarily want to replace the words, but if you really need to make an important decision on it, I think the information should be clear. So if you then use a word instead of a number and the word is just misinterpreted, then you base your decision on incorrect information. So in that case, we should make sure that the information that we intend to communicate is communicated. And then maybe words are not the best way to go, because then the interpretation of the patient, in the doctor-patient example, might be different than what you intend to communicate. So if words work fine in the situation, and maybe it's not a big life decision, then sure, use the words, and we don't need to get add a number to it. But if it's an important decision, then I think it's important to communicate the right information. And if you have probability estimates, then it would be good to communicate them either with words, but then check what this means for this person. Like maybe ask back, like, it's likely that you will experience side effects. What do you think likely means, or something? Maybe in more conversation style. Check whether the information that you try to communicate is actually is also the way it's perceived. Let's say. So yeah, but don't don't stop using words. But it really depends on the situation, whether you want to use words or numbers, I think. Yeah. Marianne?
Thanks. Yeah, I think we take the last question now, and then we'll let you speak a little further, because I just want to have it as well. Yeah, Marianne, please.
Yeah, I have a question, because I'm a PhD student, but I'm also a teacher. And what advice would you give me as a teacher? So what would you recommend? Of course, I understood what you said about numeracy, and but would you recommend, for example, to take your study to class, to talk with the students about the results, to raise an awareness? But would that be a step in the right direction? And what else would you recommend?
I think raising awareness is a good thing. That's also the main point, I think, of our study, that people are aware that if you're using the words, that you may interpret it differently than another person, so that you should double check if you understood what they meant. Yeah. And I think my recommendation would be, like, don't use words as the baseline in important life decisions, like as a doctor, or maybe in the first meeting, but later include some statistics, see how much your patient can handle, and then explain more about it in that way. Yeah, I think that's my recommendation for now. Just don't focus on words only, or check if the actual information comes across. That's the important thing. And if that's okay in words, then use words. But if you need more precision, or if you need to double check, then double check.
Thank you.
Thanks. Thanks,
Okay.
Sanne.
Then I'll move to the second. Oh, yeah. I lost you. Yeah, I see you again. Okay. So the second study that I will talk about is about misleading graphs, and especially a way to debunk them. And this is in collaboration with Jonica Smeets again, but also Peter Burger, who works at News Checkers. I'm not sure if you know it. It's from Leiden University. They check the news. They use fact checks for the news. And he also studies, does research in new media. And together, we do this together with Winifred, who is our postdoc working on this project, which is funded by Leiden University Fund. You may have seen fact checks on social media, for example. It's getting more and more common because we have so many misleading or misinformation and misleading articles, that there's more and more news fact checking going on. So the news checkers are the fact checkers from Leiden University. They really set up a website and they fact check the news, and then sometimes they regularly have an article and they indicate whether this information was correct or not, and they explain why. And this happens more often. So there are more collaborations who do this. So this is done regularly, but there's also guidelines developed on how to do fact checking. But most of those guidelines are for textual information, or to fact check photos, whether photos are correct. And some of the guidelines are like, do not repeat the message, because then the message will just stick. and also use short messages instead of simple retractions. But what is missing is guidelines for misleading data visualizations. So there's also a lot of misleading statistics going on, especially, or for example, in visualizations, and there's no guidelines yet for on how to fact check those and what would work best, how you should fact check them, how you should correct them. So that's what our study focuses on. So let's have a look at some data visualizations. Some are just clearly wrong. They, if you look at them, there's just no, you have no idea what the person was thinking. For example, this one, this is 3,200. This one is 4,000, and this one is in between 3,800 and the 4,000, but it's 3,500. So it's just, yeah, you just really don't know what happened. Just this really wrong data visualization. Also, I'm not really sure what they try to indicate here, because this is 5% and 15.2%, but usually we use a circle and it should then add up to 100%. So it's, I would say it's wrong. Maybe it's misleading because it's not what you expect of a circle, of like a pie chart. And there's also visualizations that are in principle correct, but they are misleading. So this is an example. It indicates the cumulative cases of COVID. So it indicates how how many extra cases are added every day. And this is, so it starts at 70% and then it drops to like 20% and then in the end to 10%. But this is the number of new cases. So in it's the increase. So it's still increasing because it's still above 0%. So the number of cases increases, but it looks like a downward trend as if they are decreasing. So it's kind of misleading because the message that you see is different from what you should interpret. This one also has a downward trend. It's about the number of the percentage of tested cases, but it has a downward trend. But the actual the items on the horizontal axis are the states in the US. So they are just ordered in like from a high value to a lower value. So the ordering doesn't make sense, but it seems as if there's some downward trend going on. But it just doesn't have a meaning because it's just different. You could have chosen a different ordering, and then you would have a very different plot. So I would say that there's a slight difference between really wrong statistics and misleading statistics. But there are very many different ways on how to, they come in many different shapes, let's say. So I wanted to try it with you. I wanted to make 2 groups, but since we are a small group, then maybe just stick with everyone goes for group 1. Then or maybe do both. That might be nice. Maybe you can do both. Then we can compare your 2 answers. Although, yeah, okay, I might be giving it away. Let's see.
So we're starting all in group 1.
Yeah, let's go for group 1.
Good. First, right?
And I hope this works. This is the first time that I do this with a figure. But you should see a figure and then something to answer.
Show us numbers a little longer, at least for me.
Sorry, Deb?
Could you please show the numbers again?
Oh, sorry, yeah.
Yeah. At least I haven't yet managed to put it in. So we put just the first one at first.
Yeah,
the
6
and 8.
0, 8, 8, 4, 8.
Okay. I think we can't submit.
You cannot do anything yet?
But they say voting is closed.
Oh, wait, let me check. I will move this to my other screen so you don't see the answer right away. Or the, oh. I should open it, I think. Mm-hmm. Does it work now? Oh, I should press V. Is it open? Ah, yeah, now I see numbers coming in.
Okay, and then what do you suggest? We also immediately do the option 2?
Yes, after you do the first and also the
Okay.
second one.
Thanks
And I
for
think it
keeping-
should be open now. Yeah, it is.
Yeah, I think that it is. Yeah, okay.
Still looking for a program where this works a bit smoother.
Somehow in this company, I expect that maybe the results might be quite similar.
It is actually,
Well,
yeah.
if Sanne would also measure a response time, she could probably catch the difference.
Yeah. So let me show
And
you the
eye
results. I think
movements.
because you have a very different pattern than that we found in our study. So I'll show those results later. But maybe I can show your results also later when we're discussing the other results that we saw. Maybe that's more fun to see how different you are from our participants. Okay, so you saw the misleading bar charts probably. So the way to mislead with bar charts is to just cut them off at the bottom. So for example, here, this is a comparison of supermarkets, and then it seems like the Jumbo has a very low rating compared to Crisp, but actually they're all between 7.67 and 7.98. So it's only a 0.3 difference, but it looks way, way bigger because you would expect that Jumbo has like probably less than half of the rating from Crisp, but it's just very close to each other. So that's the way to mislead with bar charts. And that's the one that we focused on. So we want to see what is the best way to debunk this misleading graphs, and does the effect last? So hey, my examples are gone. Oh, there they are. Okay. So we selected the bar charts because we wanted to keep it simple and just go for one particular type of graph in the beginning, and we chose the bar charts. We also chose to just show 2 bars at a time and then use the omitted baseline way to mislead with those graphs. So I think the example that you just saw was this one. This is the correct graph, and then this is the misleading one because it's chopped up at the bottom, and the difference is exaggerated compared to what the actual difference is. Oh. And also we base the plots on real data. So all of what you see are actually correct numbers from the WHO. And we also included only non-contested topics so that your opinion about the topic doesn't really influence your interpretation. Then we had to select different ways of debunking these graphs. So showing a correction to a person to indicate what is wrong with the graph, or to present what is best. So usually with misinformation, there's sort of a stamp on it which says it's not correct, or it's misleading, or it's just wrong. But we were wondering, like, what do we do with the graphs? So graph reading is done in 2 phases. So the first phase is the looking phase, and it gives you the initial interpretation, let's say, so the initial categorization and quantification of the data, so your first impressions. And then the second step is the seeing. So then you really refine your initial interpretation. So you're really going to look at the numbers, the text that comes with the figure, etc. So for our debunking methods, we focused on the 2 phases. The first we came up with as a correction method was just to give the correct graph. So that's focusing on phase 1 to correct this image that there's a big difference, show the small difference by just giving the correct graph. And the other 3 are focusing on sort of forcing people to look better at the graph. So in option B, we warn them that it doesn't start at 0. In C, we just give a textual warning that the vertical axis has been manipulated, but it's not. There's no error or something to indicate what happened. But we do say it does not start at 0. And in the fourth option, they also give a warning in text. And then we just say this graph is not an objective representation of the data, and people have to think for themselves on what might be wrong with it. So these are the 4 methods that we studied. And the questions look like this. So this is very similar to what you saw. We just show the graph and then ask them, like, well, how do you evaluate the difference between these 2 groups? And then people can choose between from very small to very big. And in the middle, we have a neutral point. And this is visual analog scale. So I think in the Mentimeter that you just did, you saw the number going up from 0 till 100. But that's not what our participants saw. So the number was not included. I couldn't exclude it in Menti. So you could maybe remember what number you chose in the end and then repeat it in the next one or maybe change it. But that was not possible for our participants. So these participants, they were recruited via Prolific, which is a website where you recruit participants, you just pay for them. We recruited 441 participants from the USA, and they were a representative sample, at least representative on gender, age, and ethnicity. And we showed them many graphs. So the graphs were either misleading or accurate graphs, so the correct ones. We did measurement at different stages, and we also did repeated measurements on the same graph, so in the same context, but then misleading and correct case. So, for example, all the index 1, 2, 3, 4, that indicates the context of the graph. The green check indicates that it was an accurate graph, so the correct information, not misleading. The cross is indicating that it's misleading, and then the combination of the cross and the check is the correction. So in that case, it's our correction. So at the baseline, we did a baseline measurement. We showed everyone 4 correct graphs and or 4 accurate graphs and 4 misleading graphs, just to get a baseline measurement on how much they were misled. Then the second phase was the treatment. So they saw 4 graphs again, so the same context, the original ones that were misleading. They saw those again, but with the correction, one of the 4 options. And then right after those corrections, we showed them new graphs, again misleading and correct graph or accurate graphs, to measure if they sort of learned from this. Then we waited a week. And after a week, we invited them again to participate, and we did the same thing. So we repeated the original graph, so context 1 up until 8 that they saw in the beginning. They just showed them the same graphs, and then also a set of, again, completely new graphs, which were either misleading or accurate, so that we can compare for the same context whether this changed, and also whether the effect lasts for a week. So what I sort of did with you before was the baseline measurement, but you got the same context in both cases. We actually split it into 2 groups. That was my plan with you too, so that one group gets the misleading graphs in one context, and the other group gets the same context, but then the accurate graph, so that we could also compare between groups whether there was misleading on a group level, and we could make those comparisons. So this is the whole setup, but maybe it's a bit too detailed. But at least people saw misleading graphs, accurate graphs, and the corrections, and also after a week.
Sanne, just a very quick clarification. This delayed post-test, was it completely new graphs or again the same new graphs?
The first 8 were the same graphs that they saw at the baseline measurement, so context 1 up until 8. And exactly the same ones. So if they saw the accurate graph before, then they saw the accurate graph again. Same for the misleading.
Okay, I see the numbers now. Okay, yeah, they were completely new. Okay, thanks.
And these were completely new. Yeah. So there were a lot of plots to be made by our postdoc. She looked at a lot of WHO data. So let's look at the results, but maybe it's more fun to look at your results first, because I think you have very different from what I expected. Where did the results go? Oh, here they are. So let me see. This is the the interpretation of the correct graph, so the accurate graph without any misleadingness, and you evaluate the difference as on average as 38.8. Some think it's very large, some think it's very small. But in a misleading case, you evaluated the difference to be smaller, which is not what we saw in our participants. So you're maybe a very different sample compared to the people from the US. Because in that case, we saw the opposites. So this is a graph at all the 5 stages. Purple are the interpretation of the misleading graphs. Green are the interpretation of the accurate graphs. And the green one here is are the corrected graphs, so where you see the correction at that moment. So we see that many people were actually misled because on average on the group level, you see that the interpretation, so that the perceived difference is much bigger for the graphs that were misleading compared to those that were not misleading. So it really seems that at baseline people were really misled. For you, it was the other way around, so that's kind of surprising. So that's good. Or you're more strict? I don't know. Then we also see, so this is all on group level based on these plots, but we also run the statistical test to check whether this is really happening. And everything I say now was also like significant. We also see that there's a large correction effect at the treatment. So at the moment that people see the actual correction of this graph that was originally a misleading graph, then their interpretation also drops. It's not as small as it would be if they just saw the correct graph, but the interpretation really drops. So that's an indication that the correction is working. Then after a week, so this is the original correction at the same time point. But if we show them the same graph a week later, then the correction effect got a little bit smaller. So on average, the interpretation went up a little bit again, but we still see an effect. So there's still a drop, but it just got a little bit reduced compared to right in the moment that they see the correction. And this correction effect is also visible in new graphs. So direct new and delayed new are the new graphs, new context. And then we see that the correction effect is a bit is less strong, because at treatment, if you really see the correction, the mean interpretations are lower. But for the new graphs, the interpretation go up a little bit, but not as much to go back to the original value. So it seems that the corrections, using any of the corrections, really helps to reduce the how much people were misled. And we also wanted to look at the difference between the methods, because we want to know like which one is the best, because then that will be a guideline for fact checkers then on what method they should use. So we compared these 4 that I showed before. And then here, wow, here's my screen completely black. Yeah. So then we looked at the difference between the methods. So these are the 4 different methods. We have 4 plots for each of them. And then here we see only the results from the baseline, which is in gray, compared to the treatment. So at treatment, we see that the difference is the mean interpretation is much lower at the treatment. For especially for method A, then there's a huge drop. And for the other methods, we also see a drop, but it's not as big as for method A. So it seems that method A was the most effective, at least at the moment, to correct for this misleadingness. So that seemed to be the most effective, and we really saw that there's a significant difference between A and the other types, and among these types, there's no significant difference. But if we look at the other stages in the study, so the plot that we just saw was comparing the baseline with the treatment, so really the moment that they saw the correction. But if you look at the other phases in the study, so the baseline and direct new, for example, so the new graphs right after the correction, then you see that all the differences are much smaller. A does not have such a strong effect compared to the others anymore. And the same is happening a week later with the old graphs and the new graphs. Then there's actually, maybe C has more influence here, but these differences are not significant. So apparently after a week, it doesn't matter what kind of correction you've shown, any correction has the same effect. We also wanted to look at the influence of graph literacy. So we gave this short graph literacy scale to people. They answer 4 items in which they have to interpret or read something from a graph. And then in the end, their graph literacy measure is calculated as the number of correct answers to those questions. And we see that many people had quite a high graph literacy. And we wanted to see if there's any difference between those the people of those levels. So what we see is that at the beginning, so at baseline, it's all in the sort of perfect order. So everyone with a very low graph literacy, 0, they have the biggest, they see the biggest difference between the 2 groups in the bar charts. And those with the highest graph literacy, they see the smallest difference. So they are in the same order as the graph literacy. At treatment, the treatment seems to work best for the people with low graph literacy because they drop the most, and the others drop too, but not as much. So there's a really clear drop for the low literate, and the others also have a drop, but it's just not as strong. But then for the new graphs and also after a week, it sort of goes back to almost the original level. It's a little bit lower, but not so much. So it really seems that there is some influence at the correction itself, but it just doesn't really last that much. Also especially the difference doesn't last. But it's interesting to see, I think, that for low literate, it really has a strong effect at the beginning. But at the end, we hear that the order changes, but here the original order is, we observe the same order again, just a little bit shifted. It's a bit lower. So we think that sort of any correction method helps to debunk misleading bar charts, at least in the long run. The effect is reduced after 1 week. And method A, so showing the actual correct graph, shows the most potential, at least at correction itself. And it seems that graph literacy has some influence. So that we should maybe study this a bit more. So what we are going to do next is we are going to start another study and then focus more on the people with who we expect to have a lower graph literacy, and then see what works best for them, if we really see bigger effect there or not. And another fun thing I think we're going to do is we're going to start up the grafiekpolitie, where we sort of do the actual fact checking. If people see like a misleading graph, you can email us. And then we will do a fact check on it and then put it on news checkers with a correction. So if you find in the news, if you find a fun graph which is misleading, please send it. I think we're going to start in the new year because in December it's too busy to really start this thing up, but we're in the process to start this. So that we're actually going to do the fact checking ourselves as well. Another thing I wanted to show you is that students of ours also developed a teaching package on misleading statistics. So they made the whole teaching package for high school teachers. And it's now distributed among teachers. So hopefully this will help them also discuss the topic with teachers. Peter Kopp was actually involved in this. We asked his advice on the material. And so that's now online. You can download it or you can spread it to other people who are interested. And if you want to read more, you can, from the 19th of December, so in less than 2 weeks, it is already accepted for the journal, but then it will be online. Or you can go for the preprint now and read that, which is very similar to the actual print later. So that was the second topic. I saw a question, I think, in the chat.
Perfect. Thank you very much. Very interesting data also. Much closer to education than the first part.
Yeah.
Yeah, indeed. There is a question. Could you please speak it out?
Shall I read it out?
I was actually meaning the author, but I'm struggling to find the name.
Sepnem, I think. That would be great if I.
Okay,
yes,
yeah.
Okay. First question is: do you have any background information about the participants? Yeah, so this is about the second study, right? Yeah, so we know that they are from the USA and that they are a representative sample for the US based on gender and ethnicity and what is the third thing? Age, I think. Yeah, and we have some information on them, like education level, but we didn't ask them too many personal information besides checking the graph literacy, because that was the most important thing for us.
Thank you, because I was thinking about, I'm living in the United States for the last 7 years, and my understanding of their math experience is a little different than I think people in Europe, or I'm from Turkey. My experiences about math, so they have a lot of math anxiety, and I don't know if this population informs people in Europe or in Turkey. So I was just curious about how the population might change the findings as well.
Yeah, it could be very different in a different country. Yeah, we've focused on on USA through prolific, but it would be interesting to to also repeat this in the Netherlands or Turkey or any other. So if you're open for it, then let me know. But it could be a different, definitely. Also depending on education systems, maybe how much they learn about misleadingness or graphs in general. There might be a difference between the countries, which I think probably you know better than I. So if there are differences in education, maybe you also see this in the results in this type of study.
Yeah, thank you. Thank you.
You also had a second question?
Yeah, Marika.
Oh, please continue with the other question first.
There was another question. Let's see. While voting for the misleading graph myself, I had a feeling that I need reference points.
I don't want to take all the time.
Oh, yeah.
No, please go ahead. We have, I think, enough. You can figure it out.
Okay, yeah. So so it's about you don't really have a reference point. It's a visual analog scale running from very small to very big, and there's a neutral thing in the middle. We wanted to go for first impressions. So if we would really ask them to interpret the graph and give us a number, then we would force them to really look at the graph better than they would do when they were scrolling on social media. So that's where we use the visual analog scale, that you don't have to focus on the numbers that much. It's just more like your first perception of the graphs. And also that's the reason why we included so many graphs per survey, so 8 per round. So in the first survey, there were 8, 16, 20 graphs to hopefully that they would answer fast and not spend too much time looking at all the numbers, because that's not what you do if you see a graph on social media, for example. You just don't spend all that time. So that's why we also didn't want to ask for numbers. We didn't want them to really focus on the details. Yeah.
Thanks. Let's go further to Marika.
Yeah, thank you for the talk. It was so interesting. You mentioned you measured their graph literacy of the participants. And I was wondering what that actually measured and which factors were taken into account to determine this.
So for graph literacy, we used the short graph literacy scale, which is a scale developed by Okan and colleagues. It's not really focusing on bar charts. It shows a pie chart and an icon array, also bar charts, but also a line graph-ish. So it's a scale that's often used, but there are not that many scales. So it's not really focusing on bar charts in particular, for example, but more general graph reading.
And you also mentioned that in your next study, you're going to focus on what works for those who are not so graphically literate. Do you already know which participants are the less literate?
No, so there's no not clearly one group, but we are going to set out our study at the MBO, and then young, so students between 16 and 18 or 19 years old, the first years from MBO, because we expect that they in general have a lower graph literacy than the others. But it's not one-on-one, like lower education does not necessarily mean lower graph literacy. So it's a bit of a guess, let's say. But we also want to focus on young people because they may be more easily misled, and they have to start making big life decisions. So it's important that they learn about this as well. So we're going to set out our study, and then after gathering the data, we also give them a lesson on misleading statistics so that they know more about it afterwards.
Yeah, cool. Thanks.
Thanks. And the next one, Paulina was?
I may have two questions. The first one is, I'm one of those people who so totally dances out of the lines. I will explain why. I was thinking this graph is about deaths. And death is a serious issue. And if there is 2 people more per 100,000, it means 20 per million. And in the whole of Europe, there is approximately 1 billion inhabitants. So we're talking about a difference of 20,000 deaths. And I thought that's a lot. So never mind the graphs. I thought, what is behind the graphs? So my interpretation was probably totally different than the way you were thinking. You were looking at what is it in the graphs, where I was thinking what is behind the graphs. And that is something which I think is part of statistical literacy or mathematical literacy. For literacy, there are different kinds of levels. And it has been Ruqayya Hassan who has defined 3 levels. The first one is just looking plainly at the figures and the numbers and the heights and the lengths and the widths. The second one is to think, what does it mean in reality? What does it represent? Just like I was thinking, it's about deaf people. And the third level is the critical reflections. Are the data correct? Are they gathered by somebody who has interest in putting it wrongly? Maybe with the driving in the United States, there is an issue of speeding or less speeding, or there are many more potholes. So there might be something in the statistics in the background to that same graph. And I think that's all coming together and not really covered when we only look at what is relative or absolute.
Yeah, definitely. We don't measure all those details with this questionnaire. No. And it would be interesting to see who have like an extreme answer, like say. We did check for structural differences between these contexts, and we didn't find any. So it seems that they were at least on average interpreted similarly. But some are about death and other about less serious topics. So there could definitely be an influence for individual cases. Yeah. Would be great if they were thinking so much in so much detail about it, but it's hard to measure. So in our next study, we're also going to invite some of the students for a think aloud session, so that they will just tell what they're thinking, and then we can also analyze this, see if this is maybe going on or not. So I think that's a good addition to what we do here. You had a second question?
Natasha.
Okay.
You? Okay. Yeah, let's go ahead.
Yeah, hello. Yes, I have 2 issues. I hope I will remember both of them. The first one, you said you were going to do this with young students from 12 to 14 years old, I think, at the beginning
16 till 19.
Okay, then
Yeah.
it's the same kind of students that I teach to. And I actually did something like this in my classes. several years ago with articles from the paper and so on. And yeah, it's really hard for them to do because they don't realize those things happen, and people are actually trying to mislead other people in the papers with misleading graphs. So I think it's a really good study to do in a secondary school. So maybe you should do it in a school in Flanders too, to compare.
Compare, yeah, that would be good.
And then my second question was, did you interpret why the method A had more effects than the other ones, and why it didn't last? Because I think, because in method A, it's obvious you show the right thing, so they don't have to make it themselves. While on the other three, they have to think for themselves and reconstruct the correct graph themselves. And obviously they can't do that. So I think that's the reason why it didn't last, because they know it has to be another graph, but they don't know how to do it. I think that's the reason why they can't do it after a week anymore.
Yeah.
So
yeah, even after right afterwards. So here we really show the correct graph. But like you say, it's really hard to make this in your mind yourself. So if it's not provided, it's probably really hard. You probably know that it's smaller than you expect, but you don't know how much smaller.
Yeah, well, it's a math thing, of course, and mostly people don't find mathematics so easily. So yeah, it shows that.
Yeah,
Okay,
so I think
thank you.
that's probably the reason why A is working so much better at the correction moment. But yeah, you don't see this as a lasting thing because you just don't have the graphs anymore. Yeah.
Okay, thank you.
Thank you. And Lonika, next one.
Yeah, actually, I have two questions as well. The first is about the think aloud. I was wondering if you also thought about eye tracking, because that is what I used in my study, and that was a study with graphs. And I noticed that some students in this age have difficulties to express how they think, but you can quite clearly see it from their eye movements. So yeah, that's one thing I would suggest. And the other thing is, I was wondering if you could expect a big difference after such a short intervention. And I'm glad that you're doing another study with the real intervention with teaching, because yeah, it was only such a short thing that you did. So was it why my question behind that is, why did you expect that this would make a difference?
I'm not sure whether we expected. We just wanted to check if it maybe lasts, like people, if they are warned, and maybe it's this warning sticks for a longer time period. Yeah, so that's why we checked it after a week. But we didn't expect the effect to be like the full effect to last that long, because it's just a very, like you say, it's a very short intervention. Even in this case, they see at least 4 corrections in a row, but it's very different from what you would see on social media. You would just see one fact check, and that's it. And so we try to sort of mimic the real situation, but in a study setup kind of way. But yeah, I think it's education is more important for a lasting effect, I think, than just a fact check. Because unless you see a lot of fact checks on social media all the time.
Yeah.
So if you start a graphic politie, maybe.
Yeah, because I think one important step for having a lasting effect is probably that students or people need to reflect on it, and this is not.
No,
I'm
there's
not
no
sure
time
that.
for reflection.
Yeah,
No,
exactly. So that might be an explanation, or might be an idea for also the teaching part, that you really build in a reflection step, because otherwise you might also not find an effect.
Yeah, that's a good idea. Yeah, we still have to develop this, the teaching, the lesson for this. So it's good to take into account. Yeah. And for your first question about the eye tracking, that's maybe a good suggestion. I'm wondering, like, did you also do this at a school? Okay.
Yeah, I've been a mathematics teacher for 20 years in a secondary school. And the last 6 years, I worked with students with eye tracking on graphs. So yeah, it was with students. And they were in grade 10 to 12, so they were kind of your age group.
Yeah. Okay, I could bring it up with my colleagues, see if we can include it. But I think it is also practical issues with that. But we can see.
Yeah, right now we're looking into webcam eye tracking for that. So that would make things much easier. But Winifred knows everything about my study, so you can ask her.
Oh, okay, great. I'll tell her Lonneke told us to do eye tracking. And yeah, okay. Thank you.
Thanks. We have actually many questions, but I will take a moment to ask a few of mine, because I also wonder, kind of continue, Lonneke, how do you see this teaching phase? You said a few times, like, it's not so easy to make up it in your mind, the answer, right? So you just show the answer. And this is also related to my wondering, like, what kind of theoretical framework you are using, because I can imagine that what people need actually to do, they need to imagine how it looks like. So they need to constitute special type of perception, I would say. So what do you think about the really teaching intervention?
Yeah, I wouldn't say that like our study is not really focused on the teaching intervention as an intervention. It's more like a package deal that we offer to the teachers. Like, okay, can we do research in your group, and as a reward you will get a lesson from us. So we're not going to yet to study the intervention itself. Just give them something extra to know why we are studying this. And the lesson, will be developed by one of the science communication students. So she's really going to see what would be the best lesson setup, or how we can get as much out of it as we can, I think. But I'm not sure if one lesson is going to do the trick.
But how do you see actually theoretically the process that would help them to see the difference correctly? Because you were telling that there are kind of two stages: at first looking and then seeing. And I'm a little bit getting lost from the like cognitive science perspective. Seeing and looking, that's all perception. What is the difference?
Oh, the difference that was described in this article is that looking is really the first impression phase. So just looking at the visual, the forms, and the looking is more looking at the numbers. Where does the axis start? The title, those kind of details. And we split those two because we think that in like we focus on fact checking, like graphs on social media. That's the main focus for us. And there you probably have mostly this looking phase because you scroll through all the news feeds a lot, so you don't have that much time to go into the details of a graph. So that's why we focus on the looking phase mostly, I think. And for the lesson, we still have to think of what we're going to focus on, because that's still in development. But it's good to think of what phase we're going to focus on.
Yeah. Interesting. I think that from the perspective of mathematics education, cognitive science, the process that you're investigating would be called theoretical perception or professional vision, as Goodwin would call it, or maybe educated perception. There are a variety of terms that are used with a variety of different mechanisms supposed to be building up towards this perception. So maybe kind of getting acquainted with the literature could somehow help you in thinking what kind of processes can support students in this.
Yeah, that's a good idea. Yeah, I wrote the terms down, to the students.
Maybe, because I think that's very interesting phenomena that you have discovered. But the fact that you so far didn't manage to really help, that's also interesting, right? Because it opens up for us as educators big questions.
So how can we make it last?
How we can really make the influence, and also you show the shift with your intervention, but even momentarily, it was still far away from really treating. It was only halfway, maybe, which actually means, like, I was also reflecting, like, what does it actually mean? Because if I got, like, when I was myself looking at it, at first I was thinking, okay, they're kind of like 1-2 times bigger than another one, and then I saw it. And that was a kind of abrupt transformational moment, right? It's not like a little bit, it's either or.
Yeah.
And the fact that you had this kind of a gradual shift, I would also investigate maybe more what is actually happening at the personal level. So maybe there was some people who got, right? And then it lasts. And some people who just felt, okay, something is wrong, let me adjust it. So yes, it would be very interesting to go deeper into individual answers. But sorry for taking so much time. I also know we have Paul as the next one. Please go ahead.
Okay, thank you. Well, I'm in the train. I hope my internet is stable enough to speak to you. Thanks for your 2 interesting talks, in fact, Sanne. My comment is a bit in line with Pauline's comment, I guess, in the sense that it would be a pity from a teaching perspective if you would teach to students, make sure that your bar graph, your vertical axis always starts at 0. Because this reminds me of the famous temperature global warming graph that Trump presented a few years ago. He took like 2 centuries and temperatures started very low, I don't know, in degrees Kelvin or something. So there seemed to be no global warming at all. So whether a graph makes sense or not cannot be just captured in the graph, but it's very context dependent. And that would be my main message for teaching and for avoiding, for fostering statistical literacy. So this is a bit beyond maybe your research topic, but I think it's really important. Does that make sense to you?
Yes, there's definitely, depending on the graph type, there's different ways to mislead and how you should make your choices.
But also what's misleading in one case may be very essential in the other.
Yeah, so for example, with line graphs, you can definitely omit the baseline because you have to focus on the interesting part of your values, and sometimes the 0 is not included, like average temperature. Then, so for line graphs, I completely agree. You should not always just start at 0. But for bar charts, I think it's important because the length of the bar is really something that you perceive.
But sometimes you just want to show small variations that are relevant, and that could make you decide not to start at 0. So
but then I would maybe not use a bar chart, but a different type of graph to make it not misleading.
Possible.
So I'm.
But the main point is that the graph makes sense, and that's it.
Yeah.
If I may add another comment, referring to the first part of your lecture, there's a similar thing there. Because if between the doctor and the patient there's some misunderstanding about whether likely means 60 or 90%, the most important thing at the background, in my opinion, is that you're applying probabilities to a single specific case. So if the doctor says, well, many people suffer from stomach issues there, it could be that I have a very sensible stomach so that it might be very likely in my case. So that's also part of statistical literacy, I would say. That's very important to communicate.
Yeah, definitely. So it really depends on the context, and also it's for a patient. It's always you either get it or you don't, and the percentage, doesn't matter. Let's say, I was in the PhD defense of Ruben Vromans, and he really focused on how to communicate personalized probabilities to patients. So to really say like, okay, this is fitted to your age, your gender, and maybe your background in the disease, and then these are your percentages. And they also studied like whether you shouldn't also give comparative information, like an average patient has this probability, but you are lower or higher or similar, and what that does to people to receive that information, how it's perceived. But it's also very sensitive because you're already worried about your disease, and then you get this extra information, you see that you're worse than an average patient, and you could lose all hope. So it's also very sensitive to, you should always think like, how much do I want to communicate? What is, what should we communicate? And what can the patient handle?
Thank you. And we have Peter with maybe some very last brief comment rather than even question, because then we need to round up the seminar, unfortunately.
Oh. Yeah. Thank you for this presentation. I like it very much. I was wondering for the teaching that producing misleading graphs would be an idea. And maybe to give some subjective misleading score to a given graph. Maybe that would be some ideas to produce misleading, which is always a suggestion to teach about this subject, I think.
Yeah, that's a good idea. It's also, I think, one of the lessons in the package that the students developed. They also the students are also developing misleading graphs or misleading statistics, and I think that's a very nice way to learn about it. Yeah. So yeah, maybe for the teaching part, I could still contact some of you or the students to ask advice, like Anna and Peter, and who else was commenting on?
And Veronica, maybe she's getting to. She's
yeah,
kind
all
of
right,
a
yeah.
statistical expert here, soon to become, already is. Thank you very much, Peter. Also, yeah, I think that's nice for the teaching. We have different suggestions from different angles. And finally, thank you very much, Sanne, for the presentation. Very clear, interesting, hot topic, and it was interesting to think about it from very different perspectives.
Yeah, thank you for the invitation.
Thank you.
Fun
Yeah,
to be
and
here.
good luck in your further studies of the topic.
Thank you.
For the next seminar, if you are not yet in our list, please do subscribe to our list if you want to have news about the further speakers. Normally we are holding the seminar each second Thursday of the month, and we will let you know soon about January. So thanks again, Sanne, and I will stop the recording, and we can continue chatting a little bit as a not official part.